So quantum computer is a tremendously fast computer, a computer of unimaginable speed. So just to give you an example, I mean, certain problems a normal computer would take 1,000,000 years to calculate, a quantum computer could solve in a few milliseconds, in a few fractions of a second.
It was Richard Feynman who pointed out that no classical computer can ever perfectly mimic a quantum process. And quantum processes include things like chemistry, which is all about quantum physics. So when we have a quantum computer, we will be able to make computer models, very accurate computer models, of processes involving chemical reactions, up to and including biological reactions. We will understand much better how proteins work, how genes work, and that will have tremendous implications in developing both the chemical and the biochemical technology of the future.
Quantum computers are completely entirely different to normal computers, and they're relying on a theory called quantum physics. And quantum physics is very, very strange, there are very strange effects. And Einstein, in fact, called it spooky. So one of the things which happen in quantum physics is superposition. In superposition, something can be at two different places at the same time. So an atom can be here and over there. I can be standing here and over there simultaneously. So what we do in quantum computing is we try to utilize superposition. And so we make atoms being in two different places at the same time. Now let's go back to what a normal computer does. A normal computer has bits, and these bits encode information. So numbers and words, all of these things are just encoded into bits, which are a bit is 0 or 1. And so basically information is just written into a string of zeros and ones. In a quantum computer, instead of having bits, you have quantum bits. And so these can be in a superposition of 0 and 1. So they can be 0 and 1 at the same time. When basically solving a problem in a quantum computer, you can have all the inputs of the computer simultaneously, rather than having one input, then another input, then another input, and calculate these things one by one. All the inputs coming simultaneously are being encoded into a quantum superposition, into a quantum bit. And so now this quantum bit is then computed, and we get all the answers out at the same time. This is what makes a quantum computer very, very different to a normal computer, and unbelievably powerful.
So if you've got 10 switches in a conventional computer, that's a 10-bit computer. If you have 10 switches in a quantum computer, they're called qubits, you have 2 to the power of 10, and that's just over 1,000. So you've got a kilobit instead of 10 bits, and that's just the very beginning. That's where people are now. Imagine what happens when we've got 100 qubits in a computer.
Here at the University of Sussex, we're building a quantum computer using trapped ions. Ions are charged atoms. And what we do is we actually cool these ions down nearly to absolute zero, so to minus 273 degrees Celsius. And then we take these ions and we manipulate and we encode information into the ion. Now, the ions are actually trapped inside a vacuum system, and you can see that over there. Now, if you go on a space shuttle and you step out of a space shuttle in outer space, you have much more air to breathe than inside one of these vacuum systems. So it's literally, there's absolutely nothing in there. And then basically, using electric fields, we actually hold an ion, and we can then trap that ion using electric fields, and then we use laser beams to cool that ion nearly to absolute zero.
This protein folding problem, as it's called, being able to go straight from the underlying sequence of the protein to the three-dimensional structure, is one of the holy grails in molecular biology. And some approaches have been made to it, but the complexity, the numerical complexity of it, and the whole simulation problem has really stymied a real solution to that problem. And that's something where much more powerful computers would really help.
The bottom is where the ion is in one state. The top is where the ion is in a second state. And as you can see, we're going between the two states, and here is the point where the ion is in both states equally at the same time.
If it's going to cost you £10 million to predict the drug that was going to work, rather than £1 billion to actually develop the drug that's going to work, I think drug companies would go for that.